The broadcast is now starting. All attendees are in listen-only mode.
Good morning or good evening, everyone, and welcome to the IIDS-sponsored webinar on the short-time exposure assay. This webinar is provided as part of IIDS's educational webinar series, and as such is funded through contributions to the Institute. We will begin the webinar by discussing the rationale for the development of the assay. This will be followed by a discussion of the assay steps and a synopsis of recently published work. We will close the webinar with approximately 15 minutes of question and answer time. Before we start, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. Due to the large number of attendees, all audio other than the panelists has been muted and will remain so for the duration of the webinar. You may ask questions by using the question feature at the bottom of the control panel to the right. Click on the arrow to maximize the control panel and view the questions window. Technical questions can be submitted anytime, but will be held until the end of the presentation when they will be posed during the last 15 minutes. Any questions that are not able to be answered within the scheduled webinar time will receive a written response that will be distributed to all webinar participants, along with a PDF of the presented slides within a week. Lastly, we are recording this webinar and the question and answer session at the end. Let's get started. Today's presenters from the Kao Corporation in Japan are Takayuki Abo and Dr. Yuko Nakata. Abo-san has been working in the R&D safety science research for Kao Corporation in Japan for 5 years, with a focus on the STE test for the last 3 years. Dr. Nakata-san has been with Kao for 7 years and has been working with the STE test for 2 years. Today's IIVS presenter is Ms. Allison Hilberer. She has been with IIVS for 8 years and is the study director for the STE test. Allison has worked closely with Kao over the last 2 years to bring the STE test to IIVS. During that time, she worked with her lab team to transfer the assay into IIVS in a GLP-compliant fashion. Allison?
Thank you, Mandy. Good morning, good afternoon, and for some, good evening. Welcome to our webinar that will focus on the short-time exposure test. The STE test was developed by Kao Corporation in Japan in their quest to find an in vitro alternative to the DRAISE test to evaluate ocular irritation potential. No one in vitro assay will replace the DRAISE test, and this assay adds another in vitro tool which can be used as part of a tiered testing approach. As the name implies, this assay is a short exposure assay as the test articles are exposed for a brief period of 5 minutes. This time was selected as it more closely resembles an accidental eye exposure. This is a 96-well-based monolayer assay, which makes it advantageous in that it has a high throughput, is conducted in a relatively short period of time, and can be cost-effective. As a 96-well assay, we'll need to dilute the test articles in one of 3 selected solvents. A dilution series of 3 dilutions of 5, 0.5, and 0.05% will be prepared for each test article. Only the 5% and 0.05% dilutions will be used for the prediction model for this assay. The 0.5% may be tested as an additional information about the irritation potential. MTT dye, which measures metabolic activity of the cells, will be used as the endpoint to evaluate the ocular irritation potential. Results. For this prediction model, we're able to categorize the test article as an irritant or non-irritant, and further, we have a second prediction which determines a rank classification of ocular irritation potential as minimal, moderate, or severe. In this webinar, Kao Corporation will discuss the history of the assay in regards to its development, validations, and use as a tier testing strategy. Then I'll take you through the steps of the assay, We'll again review the prediction model, go through some sample data analysis. And at this time now, I'd like to pass this over to Abo-san.
First, thank you for giving this opportunity. So we really thank to IRDF members. Anyway, let's start my presentation. We developed the test method for assessing eye irritation. Here is shown for the points of development. First, it was considered that the contact time which the chemical or formulation exposed is short. It is known that the retention in eye is short around 5 minutes. Second, contact site is the surface of cornea in actual exposure of chemicals mostly. Therefore, we developed a short-time exposure cytotoxicity test named STE test designed for the actual exposure condition. For the progress situation, STE test will start peer review soon and promote to the OECD test guideline. Here is shown for the outline of STE test method. That is, rabbit cornea cell line, SAC cells, is seeded into 96 well plate and incubate it until the cells reach confluent. Test samples are dissolved in saline 5% DMSO in saline or mineral oil based on the solubility, then exposed to cells at the concentration of 5% and 0.05% for 5 minutes. After rinsing twice, the relative viability against vehicle is measured by MTT Assay method. It is a very convenient method. In the STE test, two different protocols are available for the classification of irritancy. If the viability of 5% concentration is greater than 70%, it will be classified as non-irritant. If not, it will be classified as irritant. We demonstrated that 5% concentration exposure of STE test was a correlation against 100% concentration exposure of Drake test. Therefore, the result of 5% concentration predicts the eye irritation potential of 100% test materials. Optionally, the eye irritation potential of test samples will be able to classify to 3 ranks based on the total score obtained from the viabilities at test concentration of 5% and 0.05%. We have investigated the predictive ability of STE test in the past. Here is shown for predictive ability as concordance between STE irritation category and GHS classification. STE irritation categories with the chemicals were well correlated with GHS classification. Resulting accuracy, sensitivity, and specificity were 87, 86, and 89% respectively. These results indicated that STE test has good predictive ability. Next, we have already performed the validation study, here shown for interlaboratory reproducibility with 25 blinded samples. This study was performed by 5 robots and controlled by Jackbank. Most of the estimated eye irritation category of test chemicals were consistent between the 5 laboratories. The concordance between all labs was 84%. These results indicated that STE has excellent interlaboratory reproducibility. We analyzed out of applicability domain of STE tests based on all results obtained in the past, including validation and pre-validation study. From the results, organic salts, inorganic salts, high volatile samples, and solid of alcohols and hydrocarbons should be excluded from the applicability domain. For organic salts and inorganic salts, they might have physical irritation that is not able to estimate by in vitro assay. For high volatile samples, they might be lost by volatilization during test solution preparation or exposure. 6 kilopascal value was defined as a threshold of vapor pressure from the result of 109 chemicals. For solid alcohols and solid of hydrocarbons, they were obtained by the analysis. Out of applicability domain is now under discussion with Ikban-Niceatan. As previously described, STE test has some limitation. Therefore, we are considering the evaluation approach of bottom-up by using STE test and the other in vitro methods. We have proposed this approach in various annual meetings as 2011. In this approach, STE test or epiocular assay is selected first by checking the solubility for STE vehicles and applicability domain. Both STE test and epiocular assay are for discriminating non-irritant from irritant, but it might be able to be assessed with lower cost by using STE tests mainly, compared with epiocular assay. Furthermore, it has been demonstrated that the chemicals of the limitation on STE test was assessed accurately by epiocular assay. Therefore, epiocular can complement with STE tests, especially on the evaluation for insoluble materials. Of course, after the classification as GHS not classified, GHS category 1 and category 2 is classified by DCAP assay. We think that this approach can fully cover the assessment for eye irritation.
Thank you, Abo-san. In 2011, CAO Japan and U.S. representatives met at IIVS for a technical training session. By that time, here at IIVS, we had already set up some of the pre-assay preparations, including cell banks, workbooks, and a protocol. CAO representatives performed technical demonstrations, and we discussed some of the technical aspects and considerations for the assay. Although we were able to obtain most of the reagents and supplies here at IIVS, there were some reagents that were unavailable. Additionally, we also recognized that there were some differences in equipment and also some of the techniques that we performed. As a naive laboratory, we recognized that we might not be able to perfectly duplicate the assay in its entirety, so it was important for us to recognize the differences that existed and if those differences could affect our results. One of our biggest challenges initially was the final optical density results with our mean procedural control as well as our blank well values. We investigated our cell counts, our MTT preparations, as well as our assay procedures to see if we could identify the problem. We were able to rule out differences in cell counting as well as our MTT preparation, and what we determined that we needed to modify our plate blotting procedure at the end of the MTT endpoint. What was happening was residual media was remaining in the wells, and upon addition of the acidic isopropanol, it was precipitating the isopropanol, causing increases in the optical density values. Once we were able to demonstrate transferability in our procedures, we moved forward with 5 reference chemicals. That was followed by 3 blind-coded final products, and eventually this led to a larger study evaluating personal care products. It was this last work that led to a collaborative effort which was presented in poster form last week at the Society of Toxicology in San Antonio, Texas. This poster, the interlaboratory reproducibility of the STE test for assessing eye irritation of cosmetic products, was an international effort between 3 contract research laboratories and Kao Corporation in Japan. The ability to assess finished products is important for any personal care product. A bottom-up approach using the STE test could be useful for looking at these cosmetic products, for example, which tend to be moderately irritating. As Abo-san mentioned earlier, the STE test could be used as a tiered testing approach. We investigated the interlaboratory reproducibility in assessing these personal care products which are commercially available. We looked at 20 formulations, and of those, 13 were identified as irritant, while 7 were identified as non-irritant by the STE test. In addition to the categorization of irritancy potential, we also rank classified the irritation potential of all of these products, and then compared all of our results between labs. As you can see in the graphic below here, we did have high concordance between our laboratories, especially for the categorization and also for the rank. IIVS, for example, had 100% concordance irritation with Kao Corporation, 95% with FDSC, and 90% with Harlan. When looking at rank, the concordance numbers dropped slightly. However, they were still very high. In this graphic from the poster, we're looking at the distribution of cell viability of those 20 cosmetic products. At the bottom here, we have our cell viability at our 5% concentration, and on the left graph here, we have our cell viability at 0.05%. Recall that these 2 numbers are being used for our prediction model, and we've identified the 70% cutoff line for both of those. When looking at these products, for example, code B, you notice that at the 5% solution, our viability is about 0%. That would make this product irritant, and then when looking at our 0.05% dilution, they all fell above 70%, which would make that a moderate irritant. This was a shampoo product. In looking at code C, this is a conditioner, you can see that all of these laboratories identified this above 70% at the 5% dilution and also above 70% at the 0.05% dilution, therefore indicating this test article would be considered non-irritant. We did have some discrepancies, specifically codes A, D, G, J, K, and R. And let's take a look at code R, for example. code K, where we have everything at the 5% dilution for all laboratories identified this as an irritant. However, you'll notice that 2 laboratories, the 0.05% dilution was below 70%, and 2, it was above 70%. So although this test article would have been identified as an irritant, the rank classification would have been moderate for 2 labs and severe for 2 others. Upon further investigation, it's very possible that the solubility may have affected the results. Here's a table of all of our test articles used, and you can see 18 total were tested in saline, 2 in mineral oil, and of those, we had some that were completely soluble and some that were uniformly dispersed into homogeneous suspensions. We believe that the solubility may have been playing a role in these differences. Moving on from our collaborative efforts, now we're going to look into the technical aspects of the assay, starting with solubility. Because it's a 96-well-based assay, it's important that we're able to solubilize our test article. The STE test utilizes 3 solvents: saline, 5% DMSO in saline, and mineral oil. And we'll always conduct our solubility testing prior to the assay so that we assure that we have the appropriate solvent utilized. In the picture on your right, what you'll notice is I have 3 different samples of a deodorant. In saline, you can see that the test article precipitated out and wasn't able to achieve a solution or a homogeneous suspension. We see the same result in the 5% DMSO in saline. However, when looking at mineral oil, we were able to achieve a homogeneous suspension. The advantages of the STE assay in terms of solubility include the fact that we can use mineral oil to test water-insoluble materials. In addition, all of our solvents do not contain any buffering or serum that would potentially interact with the test articles and possibly lessen our cytotoxicity potential. And finally, homogeneous suspensions are okay to use for this assay. Additional measures such as heating and sonication can also be used to achieve a better solubility. One of the limitations of this assay, however, is if we're not able to achieve a homogeneous suspension, we cannot evaluate our test article in this assay. The cells used for the STE test are Circ cells. These cells are commercially available worldwide, and here in the United States, we were able to purchase them from ATCC. These are adherent fibroblasts, and as you can see in the microphytograph on the right. The cells are cultured in a growth medium, which is essential media supplemented to contain 10% fetal serum, L-glutamine, and an antibiotic mixture of penicillin and streptomycin. Frozen aliquots of the cells are thawed and suspended in our growth media and incubated at standard culture conditions until we reach a confluency of approximately 50%. Prior to use in the assay, these cells will be cultured for 3 weeks and can be used for up to 3 months or passage 25, whichever comes first. Like routine passaging, when the cells are ready to be seated in the 96-well plates, they're first rinsed with a phosphate buffered saline without calcium magnesium, trypsinized, resuspended in growth medium, centrifuged, and then resuspended again for counting. 2 cell suspensions may be prepared at 1.5 or 3.0 times 10 to the 4th cells per mil, depending on the number of days that will incubate our cells prior to dosing. 200 microliters of our cell suspension will be added to the appropriate wells, while the outer wells will be filled with 200 microliters of PBS to maintain humidity. The 96-well plates will then go into the incubator for either 96 or 120 hours, depending on the cell suspension prepared. And here's a brief outline of our protocol for the dosing process. We're going to go into a little bit further detail as we move along. But again, this is a 5-minute exposure. We're going to first aspirate our wells. Then we'll add our test article treatments. And we're going to add those treatments 3 wells at a time in 7 to 10 second intervals, starting with the first 3 wells. Every 7 to 10 seconds, we'll then add our next solution, and so on and so forth, until we've dosed our entire plate, which should take approximately 2 minutes. After we've dosed all of our wells, we'll then go ahead and rinse, add our MTT for 2 hours, then our solvent, and finally our plate reading. As we prepare for the dosing process, we first want to make sure that our cells look appropriate in terms of confluency and also morphology and cell growth. We're looking to see that the cells are greater than 80% confluent, and typically we would see about 80 to 100% on the date of dosing. The plates are then labeled with the appropriate test article or control dilution. Once we've ensured our cells are confluent to be dosed and the plates are labeled, we'll move forward with our dosing process. And that's going to start with aspirating each well individually using a pasture pipette. During this aspiration, as you can see in the picture on the left, we're going to tip our plate up so that we can cool the media towards the bottom of the wells. It's important as we're aspirating that we ensure that we don't touch the bottom, as this could disrupt our cell surface. After aspiration, we're going to dose all of our applicable wells, 200 microliters per well. We're going to use a syringe, as shown in the photographs below here. The syringes allow for rapid dosing time. Here's an example of our plate map, and as you can see, T1 indicates our first test article, T2 would indicate our second test article, and T3 would indicate our third test article. The C would be our concentration, with our lowest concentration, T1, C3, and so on and so forth. We also have our positive control, saline control, as well as our procedural control, which contains growth media. In addition, you'll notice the B for the blank wells, and all of our outer wells will be filled with the PBS to maintain humidity. After the 5-minute exposure, we're going to aspirate the wells in the same manner in which they were dosed. For example, every 7 to 10 seconds, we'll aspirate our triplicate wells, wait 7 to 10 seconds to aspirate our next set of triplicate wells. We're going to aspirate them using the pasture pipette well by well, and then after we've aspirated all of our wells, including our blanks, we're going to rinse with 200 microliters of PBS, aspirate the wells individually, and do a second rinse with PBS. After our last rinse aspiration, we're then going to add a 0.5 meg per mil MTT to all of our wells. The MTT is prepared in our growth medium, and it will be allowed to incubate with the cells for 2 hours. The yellow MTT is converted into a purple color through the metabolic activity of the cells. And here you can see in the pictures on the right, we have MTT conversion of our saline control. You'll notice that the MTT conversion is fairly uniform, whereas if we move down into our positive control, you'll note that the MTT is a little bit more dispersed. Cells that are not viable are unable to convert the MTT. After 2 hours in MTT, we're then going to decant our plate and then firmly blot on sterile towels and add our acidic isopropanol. Here's our plate blot procedure, and then addition of our solvent, which will extract the MTT. We'll shake the plate for at least 1 hour at room temperature and then read the optical density at 570 nanometers. From these results, we can take our raw plate data and plug it into an Excel spreadsheet. Again, we're going to use our optical density values to determine our percent viability over our 3 replicate wells for each dilution or control. Here you can see the different test articles as well as the mean optical density for those, and then a mean percent viability as determined by the mean optical density of the test article divided by the mean optical density of our solvent control. Again, we're going to capture a mean value for our blanks as well as mean OD values for our saline and our procedural controls. Each assay and each study has several controls and acceptance criteria in place to ensure the assay validity and reproducibility. Each plate will contain a positive control, which is 0.01% SLS, a solvent control, as well as a procedural control. For the positive control, the historical database of appropriate viabilities is about 21 to 62%. For our solvent control, we're going to use that to obtain our we're going to use that to obtain our viability for the applicable test article or control dilution. The procedural control is put into place as a control for our solvents, as we want to ensure that our optical density value of our solvent control is greater than or equal to 80% of the optical density of our procedural control. In addition, to assure that we have the appropriate MTT responses, we want to ensure that our procedural control achieves an optical density value of greater than or equal to 0.3. We'll also assess 3 replicate trials for the standard deviation of viability. We want to ensure reproducibility of results, so our standard deviation of viability should be less than 15%. If an individual plate criteria fails, the trial will be repeated. If the standard deviation across 3 trials is greater than 15%, 3 additional trials will need to be performed. And just as a review again of our prediction model, as Abo presented earlier, we have our categorization using our 5 dilution to determine irritant or non-irritant, looking at the 70% viability. If it's greater than 70%, it's categorized as a non-irritant, whereas if it's less than or equal to 70%, we have an irritant. And further, we can then classify our test articles as minimal, moderate, or severe irritant based on the 5% and 0.05% scores. Quite simply, we'll get a score for our 5% as well as a score for our 0.05%, add those 2 scores together, and finally obtain a rank classification of irritation potential. And to provide you with an example of our sample data analysis, we have our test articles here, different concentrations. In this case, we tested all 3 concentrations, but only the ones highlighted in yellow were used for the prediction model. We have our mean cell viabilities for each trial, as well as our average viability, which we're going to use for our prediction model. We'll assess the standard deviation of the cell viabilities, categorize the test article as an irritant or non-irritant based on our 5%, and also come up with rank scores for both the 5% and 0.05% to get a final rank score of irritation potential. Again, 3 trials will be used in the calculations for the prediction model. Here are the 3 test articles. As you can see, test article 1 was categorized as an irritant because the viability was less than 70% at the 5% dilution. It was given a rank score of 3 based on the score of 1 at the 5% dilution and 2 at the 0.05% dilution, giving it a severe rank classification. Test article 2, again, the viability was less than 70% at the 5%, but it was greater than 70% at the 0.05%, which would give a rank score of 2, indicating a moderate rank classification of irritation potential. And finally, the third example test article, non-irritant, rank score of 1, minimal ocular irritation classification. In this webinar, we talked about the history and the methods of the STE test, and in conclusion, I think it's important to highlight its usefulness. The STE test is a relatively new assay developed as an alternative to the traditional Dre's eye test to assess ocular irritation potential. During its development and validation, it was shown to have good correlations with the GHS labeling system, with 87% accuracy during the validation of 109 chemicals as presented earlier by Abo-san. This assay can also be used as a tiered testing strategy and could be used as an initial screen before testing in additional ocular irritation assays like the BCOP and epiocular assays. Many labs have demonstrated transferability of the assay, and of recent, 4 laboratories were able to evaluate personal care products using this assay with high intra-laboratory reproducibility of results. Again, there are 2 prediction models associated with this assay, and we're able to classify and categorize our ocular irritation potential. From a regulatory standpoint, this assay has received support from the Japanese Center for the Validation of Alternative Methods and is planned for review for an OECD test guideline in the very near future. This newly emerging assay has shown great promise in its ability to evaluate the potential ocular irritancy potential of single entity chemicals as well as finished products. The STE test adds another tool to the repertoire of in vitro assays used to evaluate ocular irritancy potential. At this time, I'd like to thank the entire Cal group, especially David Cameron of Cal USA, the Cal Corporation group in Japan, Nakuda-san, Sakaguchi-san, and especially Abo-san, who I've been working with very closely to transfer this assay into IIVS. I'd also like to thank the IIVS group, Roger, Hans, and Aaron, for their continued support in bringing the STE test to IIVS, and members of my lab team, Nathan Wilt, Monica Kirchaw, and especially Nicole Barnes and Jackie Bader, who spent a great deal of time working closely with me during the assay conduct. For your information, here are additional references prepared by Cal Corporation of the validation and development of this assay. I'd like to thank you for your time and participation in our webinar series. At this time, we'll take any questions that you have. Please type your questions and we'll try to get to them as we can. If you have additional questions, we'll provide email addresses for myself as well as Nukata-san and Abo-san of Cal Corporation Japan. Thank you.
Thanks, Allison. As Allison mentioned, we will now open up discussion to address some of your questions. We have a number that have come in already. The first question we would like to start with, someone was wondering, why were circ cells selected as the test system for this assay?
I think this would probably be a great question for Cal Corporation.
Okay, we selected circ cells based on our experiences for several cornea cell lines. Previously, we have investigated the responses of several cell lines, such as circ cells and human cornea epithelial T, HCET cell line. We confirmed that circ cells responded comparably to in vivo results compared to HCE T cells. So we finally made a choice based on the response.
Okay, thank you. Early on in the presentation, a question came in that said they believed that one of the slides showed that ethanol was classified as a non-irritant. And if this is so, how do we reconcile that with the fact that ethanol is a positive control for irritation in BCOP? And is it generally considered to be irritating?
I'll first start out and say that I believe that ethanol is one of the chemicals that we have identified outside of the applicability domain for this particular assay. We're able to show it being irritating, and one of the reasons we suspect is that the concentrations that we're testing for the STE test may be too low to be able to exert cytotoxic effects. Abo-san, would you like to also add to that?
So ethanol is high volatile samples. So STE test limitation is high volatile samples, as I already stated.
Okay. The next question is, could you use other equipment for dosing? For example, a multi-channel pipette?
I think that it's possible to use a multi-channel pipette. During our initial bringing the assay into IIBS, we did start using multi-channel pipettes, and we did see good reproducibility in results. A multi-channel pipette was able to deliver probably a more accurate volume of 200 microliters. However, we did run into some challenges when dosing mineral oil and also dosing some of our suspensions, which made pipetting very difficult. And to be consistent across the board, we decided to move forward with the syringe dosing as shown to us by Cow Corporation.
Could you please further explain how solubility may have affected reproducibility between laboratories? How often did the labs take a different decision on the solvent used for the same material?
Abo-san, I think you probably have more information on this from all the laboratories. I guess I'll start out by saying I believe that all of the solvents that were used for this poster were consistent across the board. Some of the challenges or the differences came about in terms of what solubility was achieved for each group. For example, it's possible that one group may have achieved better solubility through heating, sonication, or other methods than another group, which may have played a role in the differences between the laboratories.
Thank you, Alison-san. You are right.
Have you evaluated other solvents for use in this assay?
I'll give this one over to Abo-san as well.
Okay. We have not evaluated other solvents. However, we think that 3 solvents would have a wide variety of chemicals because we have experiences that most of the test articles can be solved by at least one of three vectors.
Okay, thank you. Is 0.01% SLS considered an eye irritant, or is it just a positive control for assay reproducibility?
In this case, it's considered our positive control for assay reproducibility. During the transferability phase of the assay, we actually looked at SLS in its neat form at the 0.05% and 5%, which also came out to be an irritant, and I believe it was a severe irritant in that case.
Okay, there's a question asking for a little more explanation on the data analysis slide. They said one with 4% viability had the same rank score as one with greater than 100% viability. And could you explain that? Would you like to go back to that slide?
Yeah.
This one?
4%. So for this one, again, we're going to categorize as irritant or non-irritant based on our 5% mean cell viability. So this one is less than 70%, less than 70%. So these two would be categorized as irritants. This one would be non-irritant because it's greater than 70%. For our rank score, we're going to take the scores of both the 5% and 0.05% solutions and come up with a number of 3, 2, or 1 identified as severe, moderate, or minimal. In this case, both of these were below 70%, so this would receive a score of 1, this 2, for a total rank score of 3, whereas our 5% for test article 2 was greater than 70% at the 0.05%, but less at 5%. So this would indicate 1 and a 1 here. The sum of those would equal 2, indicating a moderate rank classification of irritation potential.
Okay, thank you. Is there a classification cutoff for discriminations between GHS 2A and 2B?
I'm going to pass this one over to Cal Corporation.
So it is difficult. So we are trying the classification for GHS category 2A to B.
Okay. Has this method been compared to the fluorescein leakage or transepithelial permeation assays, and what are the key differences?
I believe there was a graphic on the poster that I did not present, but for our intralaboratory reproducibility, we also looked at this compared to the fluorescein leakage and BCOP assay, and we saw high concordances for both of them in classifying 3 ranks as severe, moderate, or minimal, with concordances about 75 to 88% for the BCOP assay. Abo-san, do you have further information to add to that?
We think so the STE advantage is to use mineral oil and to perform the short time. That's great.
Okay, is 5% of DMSO non-toxic to cells?
Yes.
We have, go ahead, Abo-san.
Yes.
We do have controls in place for the solvent. We're looking at the greater than 80% when we take our optical density of our solvent control over our optical density of our procedural. And we've noticed that the values that we achieve are greater than the 80%, and so we don't believe that the 5% DMSO is toxic to the cells. Abo-san, did you have something else to add to that?
So nothing. Is it okay?
Okay, how do the ranking classifications relate to GHS eye irritation categories? For example, is a result of mild equivalent to GHS category 2B or not classified?
Abo-san, have your group take that one?
So, the rank classification, I'm sorry. So the rank classification is that the accuracy is 70% almost.
I think to further that, as one of the earlier slides that Abo-san presented, the 5% dilution at greater than 70% would correlate to a GHS eye irritation category of non-irritant or non-classified, whereas if you had a viability of less than 70%, then you would move into the category 2 for GHS.
Yes. Thank you, Alison-san.
How are samples diluted with mineral oil washed from the cells?
I think that's an interesting question. That was probably one of the first things when I started running the assay and I heard mineral oil. After working with 96-well assays for so long, I was a little bit skeptical myself. But we are able to remove the mineral oil. The 2 rinses and the individual aspiration of wells, I think, really helped achieve complete removal of the mineral oil diluted samples from the cells.
All right. Has this method been validated as applicable for bar soaps and cleansing bars?
Abo-san, do you want to take that one?
Yes, I can. So the detergent product it's assessed by STE test.
During our collaborative efforts, we also did have a bar soap, and we were able to shave off some of the soap and solubilize it. We had to use additional measures like heating and sonication to fully get it homogenized into a homogeneous suspension.
I think we have time for just a few more questions. Why is STE proposed to identify only GHS not classified when combined with epiocular and BCOP in a testing strategy, and not GHS category 1 as well, when it seems to have good accuracy also when used to identify serious eye damage?
Abo-san, do you want to take that one?
Hi. Just one moment. So, yes, it can be used. The results of severe irritation, rank 3, so by STE test would be almost met with GHS category 1. The accuracy was about 70% as a result based on 109 chemicals. Importantly, there were only one over-prediction among 109 chemicals.
Okay. With that, I believe we will move forward and close the webinar. I'd like to thank Abba-san, Dr. Nakata-san, Allison, and all of the attendees for your participation in the webinar today. We hope that you've gained a better understanding of the STE test and the rationale for its development and use. We would like to remind you that any questions not answered during the Q&A time, and even those that were answered, will be addressed in written form by the presenters, and the answers will be disseminated to all of the webinar participants within a few business days, along with a PDF copy of the slides. If you would like additional information on this topic, please review the poster that was presented during last week's Society of Toxicology meeting. Please visit our webpage, www.iivs.org, for information on the next IIVS-sponsored webinar. Thank you once again for your participation, and we hope to see you at a meeting, training, or during our next webinar.